Grandpa always said, if you love what you do, you never have to go to work. That's work and energy to me. Work is, it's this concept. It's everything that makes anything happen around you. Energy is just a driving force to make that work happen. It's kinetic, it's potential, it's mechanical, it's around you. It makes the toaster toast your bagel in the morning. It heats your water for that shower at night. It turns the light on when you just want to spend some quality time with a significant other in your room. It's work and energy for you.
Now, enough of this nonsense. Let me tell you the true definition of work. In physics, mechanical work is the amount of energy transferred by a force acting through a distance.
One of the most basic work equations that we look at, and that we'll start off with today, is the simple definition of work. Because work equals force times displacement, or when numerically or symbolically written out, it's W equals F times S. To describe kind of how that works, I'll do a simple demonstration with everyday objects. Here, like this oak leaf. The amount of work that's about to work on it when it falls, as it hits the earth, the force acting on it, which is F, is 9.8 meters per second. The distance is about a meter. So the work that just was applied to that leaf is about 9.8 joules.
Now, work and energy are very closely related. For example, work equals the change in kinetic energy. Now, kinetic energy is the amount of energy that an object has as it moves. The equation for kinetic energy is 1/2 mv squared. There's another form of energy. Now, this is called potential energy. Potential energy and kinetic energy are similar. They're inversely proportional. Now, as kinetic energy is what an object has as it's moving, potential is what it has stored. Say a ball is high up in the air, it has a higher potential than if it was lower. This is because the equation for potential energy is mgh, or mass times gravity times height.
To now apply that learning we just had on potential and kinetic energy, I've set up this simple ramp using a roll of Reynolds tinfoil in an America's Test Kitchen cookbook. The ramp height is 8.89 centimeters, or 0.089 meters, and the ball that I'm using as the object is a ping pong ball and weighs 2 grams, or 0.002 kilograms. When the ball is at the top of the ramp, its potential energy, given the factors before, is 0.0017 joules, or and its kinetic energy is 0 joules because it is not in motion. When the ball rolls down the ramp, as I just showed, its potential energy converts to kinetic energy. At halfway down the ramp, its midpoint, the potential and the kinetic energy should be equal. When it gets to the bottom of the ramp, its kinetic energy is at its maximum, or 0.0017 joules, because they're equal, and its potential energy is at 0. Using what we know about the kinetic and the potential energy equations, we can solve for the velocity of the ball as it's moving down the ramp, or when it gets to its final point. Because we know that its potential energy is 0.0017 joules, we can now set that equal to the kinetic energy equation, which is 1/2 mv squared. In doing so, we get a velocity of 1.3 meters per second.
Shh, he's sleeping. So there's one last form of energy that I want to talk about today, and the reason why I'm talking about this is because our challenge activity involves spring constants. This last form of energy is called elastic potential energy. Now, elastic potential energy has to do with springs and elastic bands, and it has to do with spring constants. Now, the equation for elastic potential energy is
kx squared.
Even in his sleep, he dreams about physics. Like he said, the equation for elastic potential energy is 1/2 kx squared. Now, the k in this equation is the spring constant. The elastic potential energy is equal to the work done when you pull back the spring.
Now let's review the 4 equations we went over today. The first equation is work, which is force times displacement. Kinetic energy, which is 1/2 mv squared. Potential energy, which is mgh. And elastic potential energy, which is 1/2 kx squared.